Okay, so good morning, everyone. This is a project that is part of a broader problem in which we are studying measurement theory in quantum mechanics. This is the first of the problems that we have addressed in this set of problems, and this work is in collaboration with Cedric and Abhishek. So, before I describe the precise problem, let me just recall a standard result in quantum mechanics, where the first equation is the Schrodinger equation for a single particle, where you use the potential. Here we are assuming that U is not necessarily purely real, it has an imaginary component. And if we write the continuity equation for the probability current, we get this equation. And if we assume upon integration the surface terms due to J bar vanish, then it is possible to integrate this equation first with respect to space, then with respect to time, to obtain a quantity S infinity. And this is the result of that integration. Here omega is the total space on which psi is defined. So this particular quantity S infinity we would call the survival probability. The reason for saying so is that the presence of a complex or imaginary part in the potential amounts to dissipation of the norm of the state vector. And this is the length or the norm squared of the state vector after large time. Now let me describe the model on which we have studied this problem. Here we are seeing a lattice of n plus 1 sites, and at the site 0 there is present a detector. The detector will make a measurement of whether the particle is present at site 0 or not. There is a standard measurement as defined in quantum mechanics to be a projective measurement, and this P is the projection operator at site 0, and this is the complement of the operator. And tau here is the time interval between measurements. And U is a unitary operator which basically evolves the state of the system between consecutive measurements. And this assumption says that we start with a state which is concentrated or supported on this part of the system, that is 1 to n. Then it is possible to show that after n measurements, the state vector would have this form, where U bar is basically of this type. So B is the projection on the complement of the space on which the detector lies. And therefore, the survival probability after n measurements is given by this formula. So what is missing in this model is the description of U itself, and this can be provided by choosing a Hamiltonian. And we choose this form of the Hamiltonian, where the first term here shows the coupling of the detector with the site 1, and these are just nearest neighbor hopping Hamiltonian. The form of the Hamiltonian is so chosen that it is possible to map the measurement problem to a problem of a problem in which we study evolution on a lattice with traps. So if we take this Hamiltonian and then perform the exponentiation, then we find that U bar is of this form, and here H effective comes out as this. So alpha here is the ratio of gamma to 2 gamma naught, where gamma is the coupling parameter for 0, 1 site, and gamma naught is for the rest of the sites. So in some sense, we can regard alpha as a strength of measurement. Now, this H effective can be written in a matrix form, as we know. For a two-site case, it assumes this form. For an n-site case, it will assume till n cross n, and we can make n go to infinity. Then this will be an operator on an infinite dimensional Hilbert space. And it would be interesting to study what this operator does. And that's what we do in the analysis of Hn. So here we have Hn alpha defined in this manner. And I'll come to a description of these formulae in a moment. First of all, let's see how the eigenvalues of Hn alpha depend on alpha. When alpha is 0, then this is a standard tridiagonal Toeplitz matrix whose eigenvalues are well known. So here there is a plot I have shown here. So these black dots correspond to alpha is equal to 0 on a system of 101 cross 101 sites. So as we see, all the eigenvalues are real. As we tune alpha through various values, it is seen that the eigenvalues of the operator move in the Argand plane in a certain way. And at a certain value of alpha is equal to 1, something interesting happens in the sense that one of the eigenvalues separates from the rest of the bunch, and it starts migrating along the imaginary axis. And beyond alpha is equal to 1, the remaining eigenvalues start, when you tune alpha for values greater than 1, then the remaining eigenvalues start going back up towards the real axis, and in the limit alpha is equal to infinity, the system has gone from a 101 state to 100 eigenvalues, and the remaining eigenvalue has departed to minus infinity on the imaginary axis. So these formulae here are basically the simultaneous solution of this basically gives us the value of alpha critical, that is alpha c, where this pinch off happens. And it is possible to consider these expressions in the limit of large number of sites. And so in n tending to infinity limit, we can show that the critical value of alpha where this happens is 1, and this is the isolated part of the spectrum. We expect that these values should show in further calculations, and in fact they do. So let's look at the simplest case, that is two-site, where the detector is at site 0 and there are sites 1 and 2 on which dynamics happens. So the two-site Hamiltonian gives us this Schrodinger equation, and then we can solve this using exponentiation of a Jordan form of the matrix, or either by Laplace transform techniques. And these are the survival probabilities we get for this system, where various parameter regimes of alpha for which expression takes different forms, though they are all analytic continuations of each other. And at alpha is equal to 2, the form is obtained is this. Actually, alpha is equal to 2 is a case where this Hamiltonian becomes non-diagonalizable. And using the previous expressions we wrote for this case, if we solve this system, we get alpha c is equal to 2, which is precisely the point where the Hamiltonian becomes non-diagonalizable. Now we have also simulated this this model on a lattice, say 15-site lattice, in which the initial state is corresponding to the one that is the particle occupies the extreme position, and these are the various values of alpha for which these survival probabilities have been plotted. And we notice that even in this case, for alpha is equal to 1, the decay is in the survival probability is maximum, and for weaker and stronger measurements, the decay is not as fast as here. This is a simulation for larger systems where n is 100 and 200. In both cases, we have fixed alpha as 2, and the initial position is at site 20. And then we see the simulation results for the survival probability. In both cases, we see that around at a value somewhat less than 0.7, the survival probability seems to stabilize before some finite size effects kick in. So in the limit n tend to infinity, we would expect that with this initial condition and alpha is equal to 2, the survival probability should be around 0.7. this, so I'll summarize quickly. So the same problem can be now solved for n tending to infinity. That becomes a natural lattice. And this is the equation, Schrodinger equation in this case. This can be solved using Laplace transform techniques, a mix of Fourier and Laplace transform techniques. And I will not go into description of the whole procedure, but basically what we do is that we use the previous relationship that we stated in the first slide, where we obtain the wave function at the first position and we integrate it. So because this happens because the imaginary potential is only at the first site, so only the first component of the wave function contributes. And we can calculate this thing in the Laplace space and use Clarence-Sherrill theorem to obtain these survival probabilities. And in fact, if we evaluate for alpha is equal to 2, position 20, we get this number, which is what the expected value should be, is basically. Then we can integrate this for various values of n naught, and this is for n naught is equal to 1. That is the, and this graph basically is showing how the survival probability varies with alpha for various initial positions. For n naught is equal to 1, this survival probability always goes to 0. That is, the particle starts from the position itself where the complex potential is, then it definitely goes to, in the limit alpha tending to infinity, there is no chance of survival. For other values, we see that around 1, alpha is equal to 1, there in fact, it is easy to verify that this function has a minimum at alpha is equal to 1. And this is basically a saddle point approximation to this integral. So, so that's all for the talk. Thank you.
Thank you, Varun, for this talk. If there's any questions.
So did I understand correctly that matrix that you showed for H effective with the minus I alpha and the band diagonal matrix, that one, you're saying the eigenvalue for a non-zero alpha, you don't have an analytic form for it?
We basically have an analytic form. Basically, we can start with some form of when alpha is equal to 0, and then these become functions. So they are basically, actually we have an analytic form, but that's a little complicated to write here. But we do have a form.
Yeah, I mean, because you showed these dots seem very regular, so presumably there's some nice interpolating formula.
In fact, they are basically level curves of a analytic function. So when those curves intersect, they intersect orthogonally, and the points of intersection of these two curves basically define the real and imaginary part of the phase of the eigenvalue. So the eigenvalue is basically 2 cos theta, where theta is a phase. Theta itself becomes a function of it's a complex valued function.
I see.
The real and imaginary parts are defined by an analytic function. So
by analytic functions. So for any finite n, you can do that.
Yes. And we can then use those results to obtain the
limit as n goes to infinity.
Does this generalize easily if your state is actually the state of the system entangled with something else? Because usually when you have these non-unitary models, it's a problem to generalize it to that. You understand what I'm, you have these initial states which look like delta n15 or delta.
Yes.
But what if it was delta 015 entangled with some other qubit up plus delta at 14 entangled with a qubit in down? I mean, would the same formula generalize easily for the evolution of this mixed state, or how would it work?
I would assume because of the linearity, we could in general obtain an expression for
that's because the evolution is non-unitary, and so that's why I'm worried about and so that's not modeled by good linear evolution. I mean, if you do the projection thing, that's not a good linear thing. That's why.
But eventually, we are writing a Schrodinger equation, which is a linear equation. So.
Okay.
Any further questions?
Okay, so we would like to thank Varun again with a round of applause, and